Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, and welcome to Physics with Beth and Beth. I'm Beth. We're doing this AP Physics C curriculum, which is the calculus-based. It's also equivalent to our engineering physics course, that first one, and it's the mechanics. We're not doing that E&M yet. Anyway, we're going to do the mechanics curriculum first. My colleague Beth in the last video talked to you about what a derivative is, that it is that slope of a line at any given point in time, or at any given point, I should say. Time may not be on our x-axis, but it's that slope of a line that's instantaneous slope of a line, not an average slope of a line. Okay, so that's what the derivative is. She also went through the constant rule, the power rule, and the sum rule. So I'm going to pick up from there, and I'm going to show you how we can apply this derivative into our 1D motion. We are in the kinematics unit of AP Physics C, or engineering physics, this kinematics, and we're in 1D motion. We'll be going to 2D motion in a few more videos, but this is 1D. So meaning one direction, not 1D like the band. It's one dimensional, meaning one direction. We're either moving horizontally or we're moving vertically, but not both. All right, so let's look at this. I have a position time graph, and this is ugly. It's not great. All right, but if I try to take an average of this thing, and maybe I said from this point to this point, okay, and I drew a straight line, that would be the average slope between those 2 points. And that is far from what I might want in an instant in this time right here. Okay, I wouldn't get the right answer. And in physics, we like to be exact. In engineering, we like to be exact. So lives count on it in many cases. So anyway, so let's look at this. If I have a position time, we know that this slope equals velocity, and I reviewed that in the first video when we were reviewing graphing. So velocity is the slope of that position time graph. Now, I want to be exact though. I want an instant in time, instantaneous. This would be average velocity. And actually, I'm just going to put a little average like that. But this would be my instantaneous velocity at that point. Okay? So that kind of gives you an idea of what the derivative would be for there. If I had the same kind of line that looked kind of something like this, this is not being translated into this at all. Just drawing another weird curve. Same thing, we know a velocity time graph that the slope is acceleration. All right, if I tried to pick 2 points between this, that would be average. If I wanted to pick an instantaneous time right here, an instantaneous time, I could say, right here at this point, then I would get my acceleration at that instant. Okay, and I would need a derivative to get this, a derivative to get this. So let's get started, just to make sure you understand what we're looking at. By the way, this would be the derivative of position with respect to time. This instant acceleration would be the derivative of velocity with respect to time, is how we could say that. Derivative of velocity with respect to time, derivative of position with respect to time. All right, I have a problem. We're just going to jump right in. You've got this. You saw the last video. You know the constant rule, the power rule, and the sum rule. We're going to jump right in. I want you to find position, velocity, and acceleration at 2 seconds for all 3 of these position with respect to time equations. I have an equation for position here. Okay, position's easy. All I'm doing is putting 2, because for all of them I want it at 2 seconds, at that instant in time at 2 seconds. I'm just putting 2 in here. So my position is going to be 2 times 2, which is going to be 4 meters. Okay, easy peasy. Now my velocity, I'm going to need to take the derivative. I can't do an average here. I'm going to take the derivative, and I'm going to say the derivative of position with respect to time. And I'm going to go ahead and write this out so you can see it. My equation is 2t. I'm going to leave the 2.0 out, knowing that's 2 sig figs, but not to confuse you when we're starting these problems, okay? And that's going to be with respect to time. Now, that t, if you remember from the power rule, that 2t is like saying t to the first. So how do I do that? I'm going to go ahead and bring down that 1 in front of the 2. You bring your exponent down in front, so there's my 1 times what already is there. And then I subtract 1 from that exponent. So this is 2t to the 0. Because 1, I subtract 1, so 1 minus 1 is 0. Okay, well what we know about that, and I'm going to go ahead and write it out here now, is 2t to the 0. T, my variable, to an exponent of 0 just equals 1. So this whole thing right there is just equal to 1. So it's 1 times 2. All right, so it's 2. I'm going to go ahead and write this out so you can see it. 2t to the 0, which is the same thing as 2. This is velocity, though. It's going to be meters per second. And really, in these equations, you would see that they would put a little bracket around this and tell you it's meters. Put a little bracket around this and tell you it's meters, because these are all meters. All right. So when I came up with this 2t to the 0, that's in meters per second. All right, perfect. So that's my velocity. So now I have my position and I have my velocity for this A, the first equation. I put boxes around it. By the time you're doing some of this calculus stuff, it's like a work of art. Frame it, because your professors, your TAs, whoever is grading your test, your instructors, they're gonna appreciate those boxes around answers. I promise you that. Okay, now the next thing, the acceleration, is we said, hey, acceleration is the derivative of velocity with respect to time. It's the derivative of velocity with respect to time. We also can call it the second derivative of position, because it is. There's the first derivative and then the second derivative. So sometimes you'll see acceleration referred to as the second derivative of position with respect to time. Sometimes you'll see it referred to as the derivative of velocity with respect to time. They mean the same thing. Second derivative of position with respect to time is 1, 2. Or derivative of velocity with respect to time. All the same. Okay, now I know that I had, my equation was 2t to the 0. That was my equation. And let me go ahead and put a little box around that for meters per second. So what I'm saying is that my velocity with respect to time is equal to 2t to the 0 meters per second. And oftentimes you would see that written as just 2 meters per second, because t to the 0 is just 1. All right, well now I want my acceleration. I'm going to go ahead and erase this and just add this a little bit later here so we don't get confused. So now I want my acceleration, and that's going to be that derivative of velocity with respect to time. So my equation for velocity is just the derivative of 2. With respect to time. Okay, if I were looking at that on a graph, my velocity time, I put it over here. If my velocity time is just 2 meters per second, we know this. That's constant velocity. And constant velocity means that acceleration, therefore, acceleration is equal to 0. And my colleague Beth told you that if you have a constant and you're trying to take the derivative of a constant, it's just 0. So my acceleration, if I were to take this derivative of 2 with respect to time, it's just going to be 0 meters per second squared. Now, how do I know that? Well, let's go back to this t2. We said, hey, the velocity is really 2t to the 0. 2 times time to the 0. If I bring that 0 down and look at it from a power rule, and then I subtract it from 1, well, anything multiplied by 0 is just 0. So my acceleration, when I try to do the power rule on this, is just 0, which we said, hey, yeah, that makes sense, because our graph would have said 2 meters per second, constant velocity, means acceleration is 0. All right, perfect. Okay, let's move on to another one. Now that we've done A, we're gonna go do B. All right, so I have a position time graph here, and let me rewrite this over here so that we can see it, is 2t to the squared. Now this is 2.0, but I have t to the squared, and that's going to be in meters. They're going to make sure that you know that unit. All right, first thing they want is position. All you do for position is plug in 2 seconds for your t. So that's going to be 2 times 2 squared. That's 4 times 2. That's 8 meters. And that's really going to be 8.1. And I really should have done, in the earlier problem, when I said velocity was 2 meters per second, should have been 2.0. Don't drop off the sig figs. They're still important this year, like I did. That was very poor of me to drop that off. So now that's x. My position is 8 meters. I'm done. I have an answer. The next thing they want is velocity. I'm going to take a derivative of that position with respect to time. So I have my position time graph, my position time equation is 2t squared. I want to take, for velocity, to get velocity, the derivative of position with respect to time. That's going to be the derivative of 2t squared with respect to time. Now, I'm going to, this is a power rule again. All right, I'm going to bring that, my velocity, I'm going to bring that 2 down, bring the exponent down. I already have a 2 here, and then I'm going to take that t and subtract 1 exponent from it. All right, so my velocity is going to equal 4t, and 2 minus 1 is just the 1, and we're going to leave that off and just put 4t. They're going to put a little bracket around it, make sure that you know that's meters per second. So now I have an equation, and it's going to be a velocity with respect to time equation. Because the first thing they're going to do is ask for an expression. The second thing they're going to do possibly is ask for a number. Now, everything's at instantaneous time of 2 seconds. I put 2 in, and I end up with 8. 4 times 2. Write that down so we don't skip a step. Your velocity, 4 times 2, is going to equal 8 meters per second. And I'm going back to that 2 sig figs because that's what I've got. So it just so happens that my position is 8 meters and my velocity is 8 meters per second. That's just a coincidence. All right, so don't think that's always going to happen. Now I'm going to go to my acceleration. They want acceleration now. Okay, that's part C. I have my position, my velocity. Now they want acceleration. We know it's the derivative of velocity with respect to time. I go back to this velocity time equation. It's 4t. So I'm going to be taking the derivative of 4t with respect to time. All right, so here we go. That is 4t to the 1. So it's going to be, the derivative of that is going to be, I'm going to bring that 1 down, the exponent, because that's like saying t to the first power. Bring that 1 down times 4, and then I'm going to subtract 1 from that exponent, and my acceleration ends up being 4 times t to the 0, which we know that time to the exponent of 0 is just equal to 1. This thing is just equal to 1. So your acceleration is going to be 4.0 meters per second squared. And that's how you would use derivatives to get the position, which you didn't have to do a derivative, you just had to put in your time, because I gave you the position equation. Then how to get velocity with 8, and this would have been the expression. This would have been the actual answer. My expression here would have been just the same, 4.0 meters per second squared, because it's constant. All right, now, how would I have known from the very get-go that my first equation, which looked like this, I believe, was constant velocity, and that this expression was constant acceleration? Because look, this is saying acceleration is just 4.0, this is 4. that this is constant acceleration. And this is acceleration time graph, that's 4 meters per second squared, and that's constant. How would I have known that from the get-go? Your variable, your time variable can give you a clue. If it's to the first power, then that means when you take the derivative of that, you're going to get a constant, because that t is going to be going to t0 when you take the derivative. I would know immediately that this is going to be constant acceleration, because the first derivative is going to give me t to the first power right down here. The second derivative is going to give me t to the 0, which is 1, so that's constant. So your time here can be your clue. Now, here is a little thing that they do to be just a little bit tricky. If I were to give you a position, let's say I give you a position equation, and I say that it's 2.0 to y squared, and I ask you to find velocity. You can't do that with that equation, okay? It needs to be time, because remember, velocity is position with respect to time. That means time, t, needs to be your variable in these equations in order to get your velocity and your acceleration. Let's do one more that's a little bit more complicated, because it's the sum rule. That's all been the power rule. Let's do a sum rule, and I erased it, so let me put it back up. I have position is 6.0 t, am I gonna do this one? Yeah, t squared plus t 2.5 t squared. Actually, let's make that to the 4th. Okay, perfect. All right, now I have 6.0 t time to the 4th power plus 2.5 time to the 2nd. Let me make sure I have that plus perfect. Okay, first thing, if I want position, all you have to do is put time in to get your position. That's going to be 6 times 2 to the 4th plus 2.5 times 2 squared, and that ends up being your position. If you were to do that math, your position is 106 meters. Now I'm going to do the velocity. I'm going to take that derivative of position with respect to time, and that's going to be my velocity. So that derivative would be 6.0 t to the 4th plus 2.5 t squared, and that's going to be in meters, of course, with respect to time. Okay, this is the sum rule. You just take the individual pieces here and take the derivative of that. So I'm going to, my velocity, I'm going to bring that 4 down, 4 times 6, and I'm going to take that 4 minus 1, that exponent minus 1. All right, plus I'm going to bring the 2 down, 2 times 2.5, and I'm going to subtract that exponent by 1. And now I'm about to get a velocity equation. All right, I'm going to go ahead, and that's velocity with respect to time. So that velocity with respect to time, that's 24 t cubed, 4 minus 1, plus 2 times 2.5 is 5t to the first power, or 5t. All right, now that is my expression. I'm going to go ahead and block parentheses here and put meters per second so that I know my unit. Now all I do is put in 2 for my time to get my velocity. My instantaneous velocity now would be 24 times 2 cubed plus 5 times 2, and that should give you 202 meters per second. So that's my instantaneous velocity. Here is my velocity with respect to time equation, and there's my actual instantaneous velocity at 2 seconds. Now, once I took the derivative, if they said, hey, okay, now go find velocity at 4 seconds, well, then I just put 4 cubed and 5 times 4 here. And then you can get it at any time once you have this expression. Perfect. All right, we have x. All right, now we're going to do acceleration, and then we're done. We have the derivative of velocity with respect to time. I'm going to take this expression here for velocity, which is 24t cubed plus 5t, And I'm going to take the derivative of that with respect to time, that velocity. All right, I'm going to go ahead. This is my time equation. I'm going to bring that 3 down times 24. I'm going to take the exponent minus 1. That's a 1, t to the 1, so I'm bringing that 1 down, 1 times 5. And then t1, again, subtracting that 1 from the exponent. So my acceleration, that's going to be 72 t squared plus 5. Because t, 1 minus 1 is t to the 0, t to the 0 is 1. And then we have 1 times 5 times 1, which is 5. That's going to be in meters per second squared. And there's my acceleration with respect to time equation. So now you give me any time, I can tell you the acceleration. How cool is the power of a derivative, right? I mean, you can literally come up with an expression that at any time you can tell me exactly what the acceleration and the velocity is. Very cool. Now I'm going to go ahead and put 2 in for my t because I want an instantaneous acceleration at 2 seconds. That's going to be 72 times 2 squared plus 5. And my acceleration is going to be 293 meters per second squared. And now you have officially used your new knowledge on derivatives to explain and find motion equations for 1D kinematics. So excellent, way to go. Thank you for watching and hanging in there. You're gonna do awesome this year. I have absolute faith. And thank you for watching and happy physicsing.